Hi everyone, Tina here, and today I'd like to talk about hypothesis testing. Hypothesis testing is using statistics to decide whether or not there's enough evidence to reject a hypothesis or a statement of something which is believed to be true. Specifically in this video, I want to talk about hypothesis testing involving the product moment correlation coefficient, or PMCC, and the normal distribution. You'll come across both of these ideas in year 2 of your A-level course. I have made another video on hypothesis testing in year 1 with the binomial distribution, so I'd recommend you watch that video first if you haven't already. Point out the different types of question you can get asked first, and then we'll go through an example of each one. So these are the types of year 2 hypothesis testing question you can be asked. You could be asked about the PMCC, and that could be a one-tailed or a two-tailed test. Or you could be asked about the normal distribution, again one-tailed versus two-tailed. As a reminder, one-tailed tests involve less than or greater than inequalities, and two-tailed tests involve the not equals to symbol. Let's start with a PMCC hypothesis testing question, and this is going to be a one-tailed one. So it says the temperature and the number of hours of sunshine on 12 days is recorded. The PMCC is calculated to be R equals 0.636. Stating your hypotheses clearly, test at the 1% significance level whether there is a positive correlation between temperature and hours of sunshine. So we should start by stating the null hypothesis, which in this case is going to be rho equals 0. So we use rho for PMCC. And H1, in this case, we're testing for a positive correlation. So let's put rho is greater than 0. This is a one-tailed test. So our significance level is going to be 0.01 from the 1%. The next thing I like to write down is what the sample PMCC was. And in this case, it's 0.636. And that's just coming from the question there. And then we need to find the critical value for the test. So to do this, you need to look in your formula book for the PMCC table. This is from the Edexcel formula book, but you'll find something similar in yours. We need to look for a significance level of 0.01 and a sample size of 12 in this case. And that tells us that the critical value is 0.6581. So let's make a note of that. Critical value, 0.6581. And that's from the table in the formula book. And then we need to look at where the sample PMCC falls in relation to that critical value. So to do this, I like to draw a number line. It goes from -1 to 1 for PMCC, 0 in the middle. I like to put the critical value, 0.6581, and its negative version here, so that I can see where the region is that would be considered significant or extreme. So in that case, it would be these two areas here. These would be considered as significant or extreme. Anything observed that falls within the minus 0.6581 to positive 0.6581 would not be considered significant or extreme enough. The sample PMCC would be here somewhere, 0.636. So that means not significant or extreme enough. All of that is my working out in terms of what you could actually write in the exam for your conclusion. You could say something like 0.636 is less than 0.6581, therefore insufficient evidence to reject H0, i.e. not enough evidence to suggest a positive correlation between temperature and hours of sunshine. Remember, with hypothesis testing, you always want to make a comment in the context of the question. Example 2, again PMCC, but this time a two-tailed test, says Aurelia wants to find out if there is a correlation between daily maximum relative humidity and daily mean pressure. She takes a sample of 14 days and finds a PMCC of negative 0.55. Carry out a hypothesis test at the 5% significance level. So in this case, the null hypothesis is going to be rho is equal to 0 again. That's always the case for PMCC hypothesis testing. But H1 is going to be rho is not equal to 0. Because it doesn't state whether Aurelia thinks there's a positive or a negative correlation. She just wants to find out if there is some kind of correlation. Not equals to symbol means it's two-tailed. So we have to remember to divide the significance level by 2. So in this case, significance level will be 0.05 divided by 2, 0.025. The sample PMCC given in the question, in this case, is negative 0.55. And again, that just comes from looking at the question there. And then it's time to find the critical value. So again, using the table in the back of the formula book, significance level is 0.025, sample size is 14, means the critical value is 0.5324. I then suggest you draw a number line to help you decide on next steps. So -1 to 1, 0 in the middle. Critical value is 0.5324 and its negative version. Means anything outside of this would be considered significant or extreme. Anything inside, not significant are extreme enough to reject H0. The sample PMCC in this case is negative 0.55. That is significant or extreme. So we would write negative 0.55 is less than negative 0.5324, means there is sufficient evidence to reject H0. So in this case, there is enough evidence to suggest that there is a correlation between daily maximum relative humidity and daily mean pressure. Moving on to normal distribution hypothesis testing, let's start with a one-tailed test. So example 3 says the weight of a tin of beans produced by a company is normally distributed with a mean of 415 grams and a standard deviation of 3.4 grams. The company suspects that the mean weight of tins produced from a certain machine is lower than it should be. A sample of 20 tins is taken and the mean weight is found to be 413 grams. Carry out a test at the 1% significance level to test this hypothesis. A normal distribution, H0 is going to involve the mean, and in this case, the mean is equal to 415 grams normally. Alternative hypothesis is that the mean weight produced by a certain machine is lower than it should be, so less than 415 grams. Again, this is a one-tailed test, so the significance level can stay at 1%. I then like to write down if H0 is true, then X is normally distributed with a mean of 415 and a standard deviation of 3.4. Remember, with normal distribution, you put your mean mu there and then sigma squared, standard deviation squared there. For normal distribution hypothesis testing, we now need to think about something called the sample mean. The sample mean generally is denoted with an X bar or a letter bar, whichever one you're working with, and it's defined as being normally distributed with the same mean, but then you do sigma squared over n, where n is your sample size. In this case, X bar will be normally distributed with mean 415, and then it will be 3.4 squared over 20. After you write down the distribution of the sample mean, I strongly suggest you make a note of what sigma will be. So at the moment, this is sigma squared, means sigma will be 3.4 over root 20. I then always like to draw a picture if I can to help visualize what's going on. And for anything to do with a normal distribution, a bell-shaped curve is useful. The mean goes in the middle, so 415. And then in the sample, the mean weight was found to be 413. So that would be there somewhere. And this is the distribution for X bar. We're interested in the probability that X bar will be less than 413. So using less than, because that's the inequality that was in our alternative hypothesis. And this probability will be the area under the bell-shaped curve here. Using your calculator to get this, you should get 0.00426. And then we need to decide whether that probability is significant or not. So to do this, I like to draw another type of number line, this time going from 0% to 100%, but 1% on here. And I make a note to say that anything between 0 and 1% would be deemed as significant. I then see where my probability lies, so 0.00426 is quite small, it's less than 1%, which means it's significant. So we write 0.00426 is less than 0.01, significant. This then allows us to write our conclusion. So we say something like sufficient evidence to reject H0 and to support H1 that the mean weight of the tins produced from the machine is lower than it should be. For the last example, I want to show you a normal distribution hypothesis test which is two-tailed but also involves finding the critical region. So it says a machine produces bolts of diameter d where d has a normal distribution with mean 0.580 centimeters and standard deviation 0.015 centimeters. After a service on the machine, a random sample of 50 bolts is taken to see if the mean diameter of the bolts has changed from 0.580. Part A, using a 1% level of significance, find the critical region for this hypothesis test. So as a reminder, the critical region is the set of values for x for which you would reject H0. So we're going to find the observations of the diameter of the bolts that would enable us to reject the null hypothesis. Let's start part A by writing down the null and alternative hypotheses. So H0, mu equals 0.580. H1, mu is not equal to 0.580 because all it says is we want to see if the mean diameter of the bolts has changed from 0.580. So this means it's a two-tailed test, means we have to divide our significance level by 2. So we'll do 0.01 divided by 2, which will be 0.005. I would then write if H0 is true, then D, in this case, because that's the letter they've used, is normally distributed mean 0.580, standard deviation 0.015 squared. Again, you could write mu and sigma squared on top to remind yourself. I would then write down the sample mean, so D bar is normally distributed with the same mean, but this time 0.015 squared over the sample size, which is 50. Again, that is sigma squared, so it's worth writing down somewhere that sigma would be 0.015 over root 50. Now if we draw a bell-shaped curve for D bar to visualize what's going on, we know the mean in the middle is 0.580. We want to find the critical region. It means we want to find the two values for which the probability on either side is 0.005. So if we just highlight those parts, each of these probabilities needs to be 0.005. To find these values, you can use your inverse normal function, and you should find them to be 0.575 and 0.585. And those will form your critical region. So you can say critical region is anything where D bar is less than or equal to 0.575, or D bar is greater than or equal to 0.585. For part B, it says the mean diameter of the sample of 50 bolts is calculated to be 0.583 centimeters. Comment on this observation in light of the critical region. So if you look at your diagram, 0.583 would be here somewhere, not inside that critical region. So you could say 0.583 is less than 0.585, so not inside critical region. This means there would be insufficient evidence to reject H0, i.e. not enough evidence to support the hypothesis that the mean diameter has changed. And that's it. That's it for now. If you found this video useful, please do remember to like, comment and subscribe to my channel if you haven't already. And do share this with anyone else that you think might find it helpful. Thanks. See you next time.